We're going to find the absolute maximum and absolute minimum values of a function f on an interval. And the function is f of x equals x cubed minus 6x squared plus 5. And the interval is a closed interval from -3 to 5. Our first step is going to be find critical numbers. In this case, what that means is we want c in the interval from -3 to 5 such that f prime of c is equal to 0. So we need to take a derivative, set it equal to 0, solve the result for x, and that'll be our critical number. Why don't you do that and then come back. Since our derivative is f prime of x equals 3x squared minus 12x, we have that x equals 0 and 4 are critical numbers for f, and they both happen to be in the interval from -3 to 5. Now what I want to do is I want to find function values. We're looking for an absolute maximum and absolute minimum for f on the interval. So I need to know what the function values are for 0 and 4. For 0, the function value is 5. That's pretty straightforward. And when x is 4, f is -27. We might think that's the end of the story, but not quite. In a previous video, we looked at the extreme value theorem, and we saw that if f is continuous on a closed interval, then there's an absolute maximum and an absolute minimum value for f on the interval. We saw this picture here where we had a graph that had a local maximum and an absolute maximum, and then a local minimum that happened to be the same as the absolute minimum for the interval. Here's the point that I'm trying to make. We just found where a derivative was equal to 0. We found it in two places, so we have an associated potential local max and a potential local min. But on a closed interval, we could have a situation where an absolute maximum or minimum occurs at an endpoint. Therefore, it's not enough just to know what the function values are at critical numbers. I need to know function values at the endpoints when we're dealing with a closed interval. Our endpoints have values of -3 and 5. When x is -3, we have that f is -66. No, we don't. It's -76, my bad. When x is 5, our function value is -20. I'm going to draw a picture. It's not going to be a graph to scale, but it will help us to see what's going on. At 0, our function value is 5. At -3, our function value is -76. At 4, the function value is -27. And at 5, our function value is -20. I don't know what our graph looks like, but it clearly goes through at least these points. I don't know, maybe it dips up here and comes back down. Maybe it goes through 5 and then it doesn't matter. What matters is that on this interval, oh, you know what? No. At 0, we have a local maximum. And at 4, we have a local minimum. But folks, what matters is that on this interval from -3 to 5, the absolute maximum value is 5. It's the largest of the ones that we computed. And the absolute minimum value is -76. It's the smallest of the ones we computed. So here's what we did. We found critical numbers and we evaluated the function at those critical numbers, right? So this is f at critical numbers. And then we found the function values at the endpoints. So this is f at the endpoints. Of these outputs, the biggest number is the absolute maximum on the interval. The smallest number is the absolute minimum on the interval. And we're guaranteed an absolute maximum and an absolute minimum on a closed interval because this is a continuous function. That guarantee comes by the extreme value theorem. I tell you that, folks, because sometimes I'll put a problem like this on a test and someone will say, there's no absolute maximum. Yeah, there is. There's a whole theorem that says so. We're going to close out this series of videos with Fermat's theorem. Fermat said that if f has a local maximum or a local minimum at c, and if f prime of c exists, then the derivative is 0. I want to make really clear, Fermat is not saying that a 0 derivative automatically means you have a local max or a local min. We've already seen that you may or may not have one of those. What this says is the backwards of it. If you know you have a local max or a local min, and if the derivative exists, then the derivative is 0. we're going to prove this. Now this statement of the theorem involves a local maximum or a local minimum. We're going to start with the local maximum. Suppose f of c is a local maximum. Then we know by the definition of a local maximum that f of c is greater than or equal to f of c plus h if h is small enough. And folks, you may be looking at this and seeing f of c and f of c plus h, and you might be thinking about a derivative. You should be, because there's a hypothesis in the theorem that f prime of c exists. At some point, we're going to use that. Well, if this inequality is true, then it's true that f of c plus h minus f of c is negative, right? All the function values near f of c are smaller than f of c, so if I subtract, I get negative. If h is positive, then I can divide f of c plus h minus f of c by h without affecting the inequality. So that divided by h is less than or equal to 0. Now I'm going to take the limit as h goes to 0 of both sides of this inequality, and when I do, because h is positive, we're looking at the limit as h approaches 0 from the positive side of f of c plus h minus f of c divided by h is less than or equal to the limit as h approaches 0 from the positive side of 0. Well, that equals 0. Now in our statement, f prime of c exists. And that means that the limit as h approaches 0 of f of c plus h minus f of c over h exists, which means that the left-sided limit and the right-sided limit have the same value, which then means that the limit as h approaches 0 from the positive side of the difference quotient is the same as the limit as h approaches 0 from both sides of the difference quotient. And since the right-sided limit is less than 0, we have that the limit is less than or equal to, I should have said, 0. And so f prime of c is less than or equal to 0. All of this followed from h being positive. But if h is negative, then I'm taking that f of c plus h minus f of c and dividing it by a negative h. And that's going to take the inequality where we wrote down less than or equal to 0, it's going to flip it. So it's greater than or equal to 0. That leads us, though, to saying that f prime of c, which is equal to the limit as h approaches 0 of f of c plus h minus f of c divided by h, and that's equal to the left-sided limit as h approaches 0 from the minus side of the difference quotient, and that, we just said, is greater than or equal to 0. So f prime of c is greater than or equal to 0. Well, now look what we've done. We've got f prime of c is less than or equal to 0, and we have f prime of c is greater than or equal to 0. It follows that f prime of c equals 0. You can see that if we replace maximum by minimum, then we will reverse the original inequality, so f of c will be less than or equal to f of c plus h, and all the same steps will give us the same result. That proves Fermat's theorem.